thank you for coming to my presentation. I'm happy to be here. Before I go into my presentation, I want to make 2 points first, and that is I was very pleased with the motto of the conference, which is sharing to lead to better outcomes, because the motto of us, and when I say us, I mean ARA, Airborne Research Australia. Oh, take it this way around, helps. This here is actually sharing is the key. If you go onto our website, you will see it all over the website, and that's exactly what we are very serious about. I'm Jorg, I'm the Director and Chief Scientist of Airborne Research Australia. What we are, because of the lack of time, I think if you really want to know the details, maybe go to our brand new website. It's all set there. So that's one thing in advance. The other thing I wanted to just say before I go into my talk is everything that I'm showing you here is 100% unfunded. So we just did it because we wanted to do it in our own right, and because we thought that is perhaps helping a little bit to giving back to the community. So my topic is we use airborne Lidar and other airborne instrumentation for looking at various things all over Australia, and I wanted to give you just one example here. So one thing, areas affected by wildfires or bushfires or whatever you want to call it have been surveyed by airborne Lidar, but there are only very few fires where a survey has happened before by coincidence and then afterwards by sort of doing it afterwards. I will first show you some examples of things that we just did after the fire, and then some results which were shown where we captured data before and after the fire. Well, I don't have to say much about the Sampson Flat bushfire again, because that's been done by the previous speakers. We flew directly after the fire 2 missions, one with airborne Lidar, which is basically poking lasers down to the ground, and you get very high resolution topography, and you get very high resolution vegetation images and things like that. Hyperspectral is, in very simple words, you use something like a camera. Everybody knows that a camera has RGB, red, green, blue. Hyperspectral has about 400 different channels, and you can do very narrow assessments of the spectral characteristics of plants. So this is just one small area of the Sampson Flat Fire, close to Millbrook Reservoir, where some areas adjacent to each other had showed, this is an aerial photo which we took during these flights, a bit burned, totally burned, little affected, partially burned. And so let's see how that looks in Lidar and hyperspectral. And that's these 3. It's about 1 kilometer long, the transect. On the left-hand side, you can see in the hyperspectral images, you see immediately where the fire was. It is a color infrared, so the, oh, shit. So this, yeah, okay. This area is badly affected. You can see that's clearly here, and this area where it's red is not affected because this is the nature of color infrared images. Healthy vegetation is red. Then we have Lidar. This is the topography of the canopy, and you can also see there that the canopy is relatively thin in the same area, so that fits very well. And you can also see in the when you plot the areas of the height of the vegetation, you can see that mostly burned was here. You can go into a different way again, and you can see the same things, but it's clear that Lidar alone is sometimes capable to distinguish burned areas from unburned, as I just showed, unless, and the reason is because Lidar gets the Lidar returns, and if the leaves are still on the trees, as they are in many cases, they're burned, but they are still on the trees, it doesn't look very different. So you really need Lidar and some spectral images to do that properly. But the combination of the 2 is very powerful. You can also generate cross-sections through the landscape. So this is about a 5-meter cross-section over 1 kilometer from the Lidar, and you can see very clearly where things have burned, because you clearly can see, even visually, that trees have burned here, and that they have a bit burned here because it's very much thinner, there's very much less structure, and that it's not burned here. You have the whole tree and canopy quite easily visible. Lidar, I explained this before, but let's just say a few more words. It works. You have a laser and a transmitter, and you transmit Lidar pulses on the ground like this while you fly along, and then you measure what comes back. So this is a schematic of it, and I mean, it's a pretty well-known principle by now, but there might still be some people around who don't know what it is. So you can see trees, the landscape, and all of that within centimeter levels. You fly along at about 300, 400, 500 meters, and you get centimeter accuracy measurements of all of this. This is, again, basically a schematic. You see, this is what most people know, which is aerial images. But you can translate this then in elevation. So to every point, there is an elevation, which you can see here. So you see a depiction of the tree. And there is also something which is called for waveform. So you can see even more what the tree does to the LiDAR. And you can get a whole image of the structure when you use these so-called waveforms. This is another example. This is not from a bushfire. This is from Tasmania, from the Huon Valley. It just shows you what you can see, what you can deduct from these LiDAR measurements. It's in the temperate rainforest in Tasmania, and you can really reconstruct the landscape in 3D. This is an 80-meter high tower, and you can even, meteorological tower, and you can even say that there is an anemometer at the top. You can see the anemometer. This was flown about from 600-700 meters above this vegetation. So let's take an example from the Sampson Flat bushfire. This is one of the aerial photos we took. And let's see how that looks when LiDAR sees this. That's what you can see on the LiDAR. So I have the aerial photograph on this side here. There is sort of an opening in the forest, which you can identify here. And that opening has just one tree in the center. The scale is approximately 20 meters or something like that here. You can also see very clearly that you have relatively trees that look unburned in that side, but they are not unburned because they only haven't shed their leaves. This was taken just a few days after the fire, so there wasn't enough wind yet, and the trees hadn't shed their leaves yet. Or the same area, the same scene in a cross-section. So this yellow line is along here, or this is along the yellow line. And when you have that data, you can, for instance, say that this tree in the center of this opening here is 13.4 meters high, and the trees on that edge are 30.7 meters high. And so you can do a statistic, for instance, what that means, not only with trees, but with any structure that is on the ground, with a grass, with crop or anything. You can also do 3D imagery of this, where you can show people how the landscape looks. Now, the second part of my talk is, as I said, this was all after the fire. Now, we also were lucky to have one small area in the Adelaide Hills, which we flew a year before the fire, because we wanted to study some other things. And then, after the fire went through, we flew it again, and then we can compare the data. It was a small area near Gumaraka, and we flew on the 6th of November 2013. That was well before the fire. Nobody knew that it was ever burned. And then on the 25th of January 2015, so 13 months before the fire and less than 1 month afterwards. We also had LiDAR and hyperspectral. And we have, in fact, more data in our archives, which we may look at in the future. But let's just look at that. First of all, this is from after the fire. So as you can quite clearly see, or sort of clearly see, here is the burned area, and this is how that burned area looked on the ground. So it was not, I would call, severely burned, like what the speaker before me showed, because there is still some things left on the green. There's even some greenery left. So it was a moderate strength fire that went through this part of the block. And this is how it looks on LiDAR and hyperspectral. On the hyperspectral only. So you can very clearly outline the area on the hyperspectral, where you can clearly see what was affected. And I use this as a measure for then trying to identify this on the LiDAR plots. This is the data from the Lidar before and after the fire. So this is the canopy of the trees in that block. So you have to look at this area here. That is the canopy of the vegetation. So it's relatively dense. Now after the fire, you can clearly see that there is a lot of gaps and open places. So you can, if you do statistics on this, and I can't really go too far in the explanations, you can identify that on an image. But to identify the areas for your statistics, you first have to also use spectral methods. And this is really one of the key outcomes of this whole thing. Or you can see it a bit blown up. So again, before the fire and after the fire. But apart from seeing that you have far more openings after the fire, which makes sense, you can also see how consistent Lidar surveys are, which are 2 years apart, because all the other openings are nearly identical, obviously apart from trees that have fallen over or trees that have regrown or have done additional things. So you can do quantitative assessments. Now, to finish off my talk, this is where I originally wanted to stop, but I thought I might as well show you one tiny little more aspect. We have this year, my organization, or my institute, ARA, we have been for 30 years within Flinders University, always independent, but more or less within Flinders University, through some really good thing, which is basically based in philanthropy. We have now become independent as a not-for-profit institute, and our goal is really that we want to work with communities like this, and we are not really looking for funding from this community at all, because I know very few people in this room would have funding for airborne research, but we rather want to make, based on the philanthropic approaches, we want to know about interesting problems which we can look into in a collaboration and then show this and make it available to everybody. All of our data for the last 30 years is totally open. It's there for the sharing. Have a look at our website. You will see what it all is. And if you have an interesting project, small or larger, especially in South Australia, send us an email and tell us what you would like to see. I could, for instance, we do a lot of trials with our airborne instruments around South Australia because we need to know how they work for other projects, bigger projects, where we actually work for money. But we have a lot of things around South Australia which may be useful for you, and we are quite happy to look into these. Like, I mean, what you just said about the Eden Valley fire, that's a typical example. Had we known that there is somebody really working on the ground seriously, we would have loved to just do a short overflight and give you the data of it in analyzed form. So just keep that in mind, and that's really all I wanted to say. Thanks a lot.
Thank you.